So welcome back to the next lecture for the spectroscopy. So from this lecture we will start with the new type of spectroscopy, which is what the vibrational spectroscopy or the infrared spectroscopy. So as the name suggests, this vibrational spectroscopy uses what, the infrared radiation. Okay, so these infrared radiations are capable of what, changing the molecules vibrational motion. Okay, so due to this the vibrational energy of the molecule changes, and how that the frequency of radiation will resulted into the change in the frequency of given molecule, that we can establish by using certain equations. Okay, so force equations and the vibrational or the angular velocity, likewise we are going to use the various terms related with these vibrational motions, and based upon that we will try to derive the relation between vibrational frequency and the radiation that we are going to use. Okay, now for the given molecule at any temperature, if you consider any temperature, there must be some sort of vibration in the given molecule. Okay, about their equilibrium position. So at any temperature the atom in the given molecule will undergo the periodic displacement from their equilibrium position. Such a displacement are simply called as what, the molecular vibration, and these are present in the each and every molecules at inherently at any temperature. So for this we need to first consider the how that molecule might be vibrated, or how many ways there are there that molecule can vibrate. Okay, so for that purpose we will consider the number of degrees of freedom. Okay, so how we can explain these degrees of freedom? So degrees of freedom are simply what, the number in which that molecule can transmit its vibrational energies. Okay, so we will be more focusing on the number of degrees of vibrational freedoms. So for that we need to first of all find out the total number of vibrations or total number of freedoms. So for that we just consider simple logic. Okay, so for the given molecule, if we consider the molecule as a whole entity, then how many ways that molecule can how many ways or how many coordinates that will be required for the given molecule to be specify its position in the space. So we will be requiring three variables, that is Cartesian coordinates. Which three Cartesian coordinates? X, y and z, right? But this is for what, if we consider the molecule as a whole entity, means suppose if we are having the only the helium atom. Okay, only the helium atom placed in the given space. Okay, so by using these three coordinates we can simply define its position in the space for the helium atom. But if we are having only the, say, simple linear molecule like say H2, okay, H2, so there are what, two atoms are there. So for this we will be requiring what, the, if we consider whole molecule like H2, then we can define it by again three variables. But if we consider this H and H atom linked by the certain bond, and they are having the certain bond vibrational. So if you want to like describe the position of this molecule like H attached to another H, then we require the three coordinates for this hydrogen atom, three coordinates for this hydrogen atom. Okay, and also we will be requiring three coordinates for the, okay, the center of mass for the given bond. Okay, so that will be also required in order to define the position. So in order to describe the position or the position of atoms relative to each other in the given atoms, so for the molecule containing n atoms, so we have considered for 1 2. So in general, if there are the n atoms in the given molecules, then there will be what, 3n degrees of freedom. So one along x-axis, one along y-axis and one along z-axis for the one atom. So for n atom it will be 3n degrees of freedom. So molecule which has a finite dimension will thus be made up of the rotational motion, translational motion and vibrational motion. So if we consider the degrees of freedom, so all the degrees of freedom are nothing but what, the summation of rotational degrees of freedom, translational degrees of freedom and vibrational degrees of freedom. So in order to know the rotational degrees of freedom and translational degrees of freedom, so since this molecule will have the three coordinates and they are necessary to locate the molecule in the given space, the molecule will always have what, three translational degrees of freedom. It is obvious, because in order to translate the molecule we must specify the three of the coordinates. Okay, now three rotational coordinates are needed. so as to specify the orientation of molecule about the center of gravity also. So these are the three angular coordinates which will specify the rotational motion about three mutually perpendicular axes, sorry, coinciding at the center of gravity or the center of mass for the given rotational motion. So there are what, 3 degrees of freedom along the translational motion, 3 degrees of freedom along the rotational motion. So we have been left with only vibrational motion, and we need to find out exactly that number of vibrational degrees of freedom. So in vibrational spectrum of the molecule, we are more concerned with the number of fundamental modes of vibrations. So each fundamental mode of vibration is corresponds to the band in the given spectrum, that is vibrational spectrum or IR spectrum, and each degrees of freedom corresponds to the fundamental modes of vibration. So therefore we are more concerned with the number of vibration degrees of freedom for the molecule. So if we are going to have the two cases, one is what, non-linear molecule, and another one is the linear molecule. So for non-linear molecule which is having n number of atoms, which shows the 3 translational degrees of freedom, 3 rotational degrees of freedom. So the expression for vibrational degrees of freedom will be what, it will be 3n minus 3 plus 3. So 3 is for what, vibration, sorry, rotational, and 3 is for translational. So formula will be 3n minus 6. So this will gives you the number of vibrational modes for the non-linear molecule. So for example, consider for benzene molecule, which is a non-linear planar molecule. So theoretically they can have what, 12 into 3 minus 6, which is comes out to be around 30 fundamental modes of vibration. And for ethane molecule, they are having what, total number of atoms are 8. So total number of fundamental modes of vibration comes out to be around 18. Okay, so for non-linear molecules, simply remember this formula for calculating the number of modes of vibration. So you might be asked about simple the you might be given the molecule. So first of all we should know the structure, okay, whether it is linear or non-linear, and based upon that we can simply predict the number of vibrational modes of for that molecule. Now consider for the linear case. Now for the linear case there is one change. Okay, so for the linear molecule having the n atoms, which is having 3 degrees of translational freedom, 2 degrees of rotational motion, so 1 degrees of rotational motion get decreased. So why is it so? This is due to the fact that the rotational motion of linear molecule about its axis of linearity does not changes due to the not change in the position of atoms. So if you consider the rotation of molecule about its bond axis, okay, bond axis, so there is no change in the position of the given atoms. Okay, so this is why, because we are considering the linear molecule case. So if we consider the rotation about the bond axis, then there will not be change in the any coordinates related with the any atom. So we just need to decrease that uh, one number. Now other two rotational modes, which are about what, two axes, which bring about the change in the position of atoms. So we have to consider that two rotational modes, but only that rotational mode which will be related with linear axis, that will not be considered here. So we just decrease the degree of rotational motion. So the expression for vibrational degrees of freedom will be what, 3n minus 3 plus 2. So here 3 is for translational motion and this 2 is for what, rotational motion. So a formula will be 3n minus 5. So for example, for the linear molecule like CO2, the number of modes of vibration will be 4 and not the 3. Okay, so this is the only change for the linear molecule. So for non-linear molecule the formula is what, 3n minus 6, and for the linear molecule it is 3n minus 5. Now next point is the modes of the molecular vibrations. So there are the two types of modes in the given molecule. Okay, so one is the stretching vibrations and another one is the bending vibrations. Okay, so if you like consider the molecule as a atom and uh, chemical bond as a ball and spring model. Okay, so there we can quite imagine that how that vibration in the molecule will takes place. Okay, so we just need to consider that atoms as a rigid balls and the bond is as a spring and not the string. Okay, so the spring can be stretchable as well as compressible, so we need to consider this bond as the spring. Okay, now when the molecule will absorb the infrared radiation, it will sets into the vibration. So the vibration in the polyatomic molecule will be of two type. One is of the stretching vibrations and another one is the bending vibrations. Now the stretching vibrations are again classified into three types. One is what the isolated one, so this is for the linear type of molecule, so vibrations will be either along the bond or bond axis. Okay, so likewise, so for isolated molecule. Now for the non-linear molecule, there might be the symmetric vibrations and there might be the unsymmetric vibration. So in symmetric vibration, what will happen? So in symmetric vibration, the net change in dipole moment will be zero. Okay, so symmetric vibration or symmetric stretching, one molecule is moving in this direction and another one or another atom in the opposite direction, so the net change will be the zero. But in case of unsymmetric one, one is moving in this direction and another one is moving in this direction, so the overall we get the increase in the vibrational motion for the given molecule. So in symmetric vibration, both the atoms are having the away simultaneously from the central atom, whereas in unsymmetrical vibration, one atom is moving towards the central atom while the other one is moving away from the central atom. So stretching vibration, which requires the higher energy than the bending vibration, and are generally denoted by the symbol nu bar. So there is one specific formula for calculate, we will see this formula again. So there is one specific formula in order to find out the stretching frequency for the vibrational motion, which is what, 1 upon 2 pi c into bracket k into nu, where k is what, k is the force constant and nu is the reduced mass for the given system. Now next is the bending vibrations. So first we have seen the stretching vibration, now we are seeing the bending vibrations. So now again the bendings are of the two types. So bending is what, either in plane bending and out of plane bending. So in plane bending is further classified as the, so here it will be quite clear. So for in plane bending means what, suppose this is our central atom and these are the two adjacent atoms. So in plane vibrations means within the plane of the molecules. Okay, within the plane of the molecules. Now there are the two types again in plane, that is either rocking or scissoring. So what do you mean by rocking? Rocking means both the atoms are moving in the same direction, and for scissoring, either first they will move into the closer to each other and then again they will move to the away from each other. Okay, so this rocking is the uh, moving of the atom in the same direction, and this scissoring is the moving towards itself and moving away from itself. Okay, now out of plane vibrations are again of two types, one is the wagging and another one is the twisting. So what do you mean by wagging? So both of these atoms are simultaneously moving in the same direction out of plane. Okay, out of plane they are moving in the same direction, that is either along this direction or along this direction. Okay, and for twisting, one atom is moving in this direction, another one in this. Okay, so this is the twisting one. So in summary, we can say that the vibrations are of two type, one is the stretching vibration, another one is the bending. Then again stretching are classified as the isolated and the coupled one, and this coupled one is again classified as symmetric and unsymmetric. And these bending vibrations are twisting, wagging, rocking and scissoring. Okay,